Very good morning to all of you. Okay, I think the LMS is down. So one thing you will do at the end of the class, Pooja, या फिर Ayushi, send me na any one of you send me the screenshot of the attendance. Okay, or I will take it. Don't worry, very less students are there. So till yesterday we were discussing about some problems on EC bridges, right? So today we will move on to the second module. So let me share the PPT with you all. Um, Second module is bit theoretical part. You will have some measuring devices. Suppose all those RMS voltmeter and let me tell you, this is the syllabus. If you follow the syllabus, you will be able to understand all these frequency meter, then high frequency measurement, then actually module 2 is again having two parts. One is all these basic parameters, electronic instruments, another is your CRO. The CRO, you are much aware of CRO, I hope so, right? The CRO, you are much aware of it. So I don't have to put much effort on CRO, but rest of the things, all those measurement parts we will discuss. Vector impedance meter, all those things. Okay. So first topic is, wait. Yeah, see, first topic is true RMS voltmeter. So we can also in exam time you can also get it as RMS, true RMS reading voltmeter. Okay, true RMS reading voltmeter. So this can be also reading voltmeter. Actually, this subject is all about the measuring instruments, right? How you can measure frequency, how you can measure voltage, all this. So look into the diagram very nicely. This diagram is important. Wait. Okay. So this is my picture and now you're able to see, I think. Now this is the diagram. Diagram is important. See here, in the diagram, first you see the diagram. That is will be enough for you. This diagram is about two RMS responding voltmeter. See what are the components here in the diagram. Okay. So that components are important. See, there are two thermocouples. Have you seen? One is measuring thermocouple and one is balancing thermocouple. Okay. So if you minutely see the picture of this true RMS voltmeter, then you can able to write about it on your own. You don't have to go through the things. So look into this. There are two thermocouples mainly named. One is measuring thermocouple and second is balancing thermocouple. Okay. So first of all, it is having two thermocouple. This is my very important part. Second is that they forms a part of bridge at the input of the DC amplifier. Okay, you see here, this is the DC amplifier. So balancing thermocouple is situated here and measuring thermocouple is situated here. So they are actually forming input of the DC amplifier. I mean AC on the output of the AC amplifier, they are connected, and so they are becoming the input of the DC amplifier. Okay, the same non-linearity effect takes place in both the thermocouples. So what effect takes place? Non-linearity effect. Okay, effect. So this RMS voltmeter are most accurately used to measure RMS voltage. Okay, or you can say it is mainly used to measure with an RMS voltmeter. So what is actually measured? Complex waveforms are measured with the help of this voltmeter. This instrument is a meter indication by sensing the waveform heating power, which is proportional to the square of the RMS value of the voltage. So this is the process. I mean how you can measure the true RMS voltmeter. Now this heating power can be measured by amplifying and feeding into thermocouple. So here is the requirement of thermocouple in this particular picture. Now we know for what reason this true RMS voltmeter is required, right? Now it comes to what is the composition or component that forms this true RMS voltmeter? First of all, thermocouples. Thermocouples are what? Non-linear devices, right? It's difficult to, and this difficulty can be overcome in some instruments by placing two thermocouples in the same thermal environment. So, as thermocouples are non-linear devices, so suppose if this kind of instrument in true RMS voltmeter, if you place two thermocouples simultaneously, then they can be balanced. So see here, as I told you, that two thermocouples are present here, measuring and balancing. Okay, and they become input to the DC amplifier, and they have a non-linearity effect. So these things are clear, that for what it is used, what measuring purpose it is used, and thermocouples here are used in non-linear devices. Now, this non-linearity effect of thermocouple, it can be compensated because of the using of these two thermocouples. Okay, so an input AC voltage to be measured is first amplified by using an AC amplifier. So you see here in the AC input voltage, it is the input part of the AC amplifier. Okay, we are giving it as an input. Now, to avoid any DC component in the measurement, a coupling capacitor is used. You will see here we will be using a coupling capacitor. Let me show you. A coupling capacitor is used at the input side. So in the input side they haven't shown here, but here a coupling capacitor is used. It is called coupling capacitor. Okay, is being used. Coupling capacitor is used. Now the output of the amplifier is connected to the heating wave. Okay, heating wave, and the output of the amplifier is connected to the heating element of the measuring thermocouple. See, here is thermocouple, here is thermocouple. So these are the inputs, and outputs are also connected to the thermocouples. Now this will generate the heating wave at the thermocouple. Okay, now this thermocouple will generate the voltage that is proportional to the heating wave. So thermocouple, what it will generate? The voltage. Okay, that will be proportional to the what? To the heating wave of the waveform. Okay, so now so this part is done. So this voltage is generated by the measuring thermocouple makes the bridge balance. Okay, here in instrumentation we have always put emphasis on the fact that whatever measurement we are doing, we have to look into that our bridge is balanced. So here also same thing, that this voltage generated by measuring thermocouple, sorry, here the bridge actually it becomes unbalanced due to this kind of heating and all. Now this voltage is amplified by DC amplifier. Now what we have to keep in our mind, that our instrument has to be balanced, but this is creating a problem. This heating wave which is proportional to the voltage generated by thermocouple, that is creating an unbalanced condition in the bridge. Okay, and that voltage is again amplified by the DC amplifier. Now the output current from the DC amplifier, definitely it will act as a feedback. Okay, feedback current. So it will create this will create a heating of the balancing thermocouple. Okay, now this balancing thermocouple will give the voltages that is proportional to the heating wave. So so a stage will be reached, at which output of the measuring thermocouple that will become equal to the balancing thermocouple. So this is my balancing, this is my measuring. So we have to always look into the fact that this output of this measuring thermocouple and the output of the balancing thermocouple, I'm writing the short form, these has to be equal. So then only the balancing of the bridge is possible. Okay, so at this point the balancing of the bridge actually takes place during that condition. So the feedback current here becomes equal to the you can say the input current, and this current is now used to cause the movement of the indicating meter. So the indicating meter, that is, see this kind of voltmeter, definitely what its final work? Its final work is to move the indicating meter, that is this meter from where we can take the reading. This is the indicating meter. Okay, indicating meter. So from this indicating meter, we are taking the reading, but all these things are happening internally in the RMS voltmeter. That is a very interesting thing. So many things are happening, but ultimately what we are doing, ultimately our work is to take the reading from the indicating meter. And for that reason, the output of the measuring thermocouple and the output of the balancing thermocouple has to be equal. Okay, so these two things are important regarding this. So a true RMS meter is always a combination of the normal value of the indicating meter, okay, and the squaring device whose output we are getting. That has to be also proportional. So it can be shown. So here are some other devices we can also attach to it for a particular reading purpose. If this instrument is to get the reading, we can connect any instrument to it, to this true RMS voltmeter to get the reading. It's a voltmeter. It will give us the voltage of any device to where it's connected. So definitely these meters should be calibrated properly, and so that we can, and obviously in the balance condition, so that we can get the proper waveform. So basically this kind of RMS voltmeter, I hope you could understand that what these are used for. These are used for measuring complex waveform, okay, whose RMS voltage has to be measured. Now our next topic, as per your syllabus, we can move on to it. Let me so this is all about, so I'm clearing this portion. I have go to the next topic, that is as per your syllabus. Let me see what is there. Next topic in your syllabus is this one, digital frequency meter. I think this is visible to you all, digital frequency meter. This chapter will be a bit boring because I know these are all boring topics, measurement and all, but I will try to wrap up this chapter soon. Okay, so don't worry. Okay, so look into the digital frequency meter. So what is that? Here's a proper definition of digital frequency meter. You can see here that a digital frequency meter is an electronic instrument that can measure even smaller value of frequency up to 3 decimal of a sinusoidal wave and displays it on its counter display. It counts the frequency periodically and can measure in the range of frequencies, this one. So this range is important. The entire concept is based on the conversion of sinusoidal voltage into continuous pulses, that is 0.110 second along a single direction. So from this definition, I know nothing you are able to understand. Only you have understood that it's an electronic instrument measure that can measure small value of frequency up to 3 decimals, okay, of a sinusoidal waveform and simply display on the counter. First, we need to know the construction of digital frequency meter. See, this kind of components or instrument, two things we need to understand. One is, what is this measure for? I mean, what is the significance? What is the significance of this device? Okay, that what it is used for. Significance of device. Significance of device. And second thing is, you can say construction part, because unless and construction and working, unless and until you learn the construction and working, you won't be able to understand. Okay, so this is the important part. So see here, first of all, look into the diagram. The diagram is clear to you, visible. So first of all, see the extreme left side, you will see here is an unknown input signal. Have you seen this? So what is this? Or you can say it is also called as unknown frequency source, because we don't know what kind of source is being given. So it can be also called as unknown frequency source. We can also call it like. So it is this unknown value of input signal frequency. It is used to measure This is used to measure the unknown value of the input signal frequency. We don't know what is that, but we are giving this kind of supply signal to the amplifier, right? Why we are giving to the amplifier? What is amplifier do? What does amplifier do? Can you tell me, anyone? What is the work of the amplifier? Come on, EC students are much aware of the amplifier. Tell me the amplifier. What is amplifier? Why we have connected amplifier here? See, if you know the basic definition of amplifier, you can tell me. Yes, tell me.
Ma'am, amplifier will give a strength increase. It will improve the signal strength.
Okay, amplify. See, amplifier definitely amplifies the signal. It allows the signal to pass through such channel through which weak signals cannot pass. That is the thing. Achha, here amplifier is used. It amplifies the low level signal to high level signal. Okay, so here low level signal is amplified to high level signal. So after amplification, that means our input is a low level signal. Okay, so here whatever input we are giving, that is low level. When it is passed through amplifier, it became high level signal. Now here I have high level signal. Now this high level signal I am passing to the schemic trigger. Okay, what is schemic trigger? So EC students are much aware of this device also. Schemic trigger is a sorry. The main purpose of schemic trigger is to convert analog signal into digital signal. Okay, in a pulse train form. So this is schemic trigger. So what it is for? Analog signal to digital signal. So simple, whatever high level signal we have formed here, then it will convert the analog signal to digital signal in a pulse train form. How? It will be just like this, pulse train form. Okay, very close pulses, very close pulses. But just so minute pulses schemic trigger have produced. So it is also known as ADC. That is why schemic trigger can be also called as ADC. Means analog to digital converter. Okay, that is why we also called as schemic trigger as ADC. And basically it acts as a comparator circuit. If you learn in EC communication, one sub chapter is there on schemic trigger where you get to learn a lot of things. Okay, so it is also used as a comparator circuit. What? Comparator circuit. Okay. Now, after schemic trigger produces this kind of trigger pulses, this becomes the input of the AND gate. Okay, so this is the total process. I mean, how the digital frequency meter works. What is the inside structure of digital meter? So from this diagram, see, you can understand the construction as well as the working, both simultaneously. Okay, now the trigger pulses which we obtain, that become the input of the AND gate. Okay, so AND gate, why it is used AND gate? Can you tell me AND gate? See, the generator output from the AND gate, it's always it's obtained only when the input exists at the gate. Suppose you can see here, one of the terminal of the AND gate is connected to schemic trigger output and another terminal is connected to a flip-flop. Have you seen here? See, there are two inputs to the AND gate. So one of the is connected to this output of schemic trigger, another is connected to this flip-flop. Have you seen? So this is the thing, that the generator output from the AND gate is obtained only when the input exists at the gate. So this is important, that the input of the AND gate, one input should be the trigger pulse and another input should be the gate flip-flop. Any flip-flop there should be there. Okay, so this is the picture. Now you can see your counter. Where are the counters situated? You can see now. These are the counters. You can see here. So what is the work of the counter? These are the counters. What is the work of counter? It is operated, or it operates based on the clock period, okay, which starts from 0. So one input is taken from the output of the AND gate. Here another counter display has been shown. Okay, you can see here. These are the time-based selector. Okay, sorry for this thing. This is the time-based selectors. This one, the down portion. This is the counter part. Okay. So what is the work of the counter? It operates on the clock period, which starts from 0, and one input is taken from the output of the AND gate. You see here, this is the output of the AND gate, and that becomes the input to the counter. Okay, and counter is constructed by cascading many flip-flops, which that's the internal structure. Now comes crystal oscillator. This you see at the down is given here, crystal oscillator. What is the work of this crystal oscillator? See, when a DC supply is given to a crystal oscillator, that is around the frequency of 1 megahertz, it's written here. What is the frequency? It generates a sinusoidal wave. Okay, so so you see here, if a DC supply gives when a DC supply is given to a crystal, that DC supply means what? Simple straight line, right? Simple straight line. If we provide to the schemic trigger, sorry, with this crystal oscillator, it will give us a sine wave. Okay, so this is the importance of crystal oscillator, and that sine wave can become an input to the schemic trigger, and then so on, and it generate the pulses. Now comes about time-based selector. These are the time-based selector. What are the use of this time-based selector? Can anyone tell me? See, you can see here at the top of every selector, there are given some 10 microsecond, 100 microsecond, 1 millisecond, 10 millisecond, 100 millisecond. So depending upon the reference, the time period of signals can be varied. Okay, it consists of clock oscillator, which can gives you accurate value. Now this clock oscillator output is given as an input to the schemic trigger, which will give us a sinusoidal wave of the same frequency. Now these continuous pulses are then sent to the frequency divider decade, and then one after another. It consists of a counter decade, and the frequency is divided by 10. That means these pulses which I got from here, that is given to each and every counter, and it will be divided by 10, each frequency. So each decade frequency divider provides respective output using a selector switch that you will get somehow here in case of time-based selector. Okay, next comes flip-flop. So EC students are much aware of flip-flop, I know, in digital electronics. So what is flip-flop? Why we add flip-flop to a circuit? Can you tell me? What is flip-flop and why we add flip-flop to a circuit? See, flip-flop are very, very important. It provides output based on input. Whatever input we are getting, our output will be just exactly according to that. Okay, so this schemic trigger pulses are again becoming the input to the gate flip-flop, and then it is becoming input to the AND gate. So what is the working principle of this total digital frequency meter? I have to concise this to you. So first of all, you see what are the components you have learned here. First of all, you are giving the unknown input signal, use amplifier, then you are using amplifier, then schemic trigger, then AND gate, then flip-flop, then counter, then crystal oscillator, and then time-based selectors. Okay, so now I will tell you the working principle. Let me discuss. Actually, I'm removing everything, okay, from here. Okay, now you see. Listen to me very carefully. When an unknown frequency signal is applied to the meter, it passes through the amplifier, which amplifies the weak signal. Okay. Now, the amplified signal is now applied to the schemic trigger, okay, which can convert the input sinusoidal signal into square wave, just like this, square wave. Okay. Now the oscillator also generates here at the down you see here, oscillator also generates sinusoidal waves at a periodic time interval, which is fed to the schemic trigger here. So this trigger converts sine wave into square wave, which is in the form of continuous pulses. Okay, when one pulse is equal to one positive and one negative value of the single cycle. The first pulse which is generated is given as a input to the gate control flip-flop. See here, this Schmitt trigger is producing pulses that is being given as an input to the flip-flop that is helping in turning on the AND gate. Now the output from this AND gate count the decimal value. Similarly, when the second pulse, so two pulses will arrive at a time. First pulse, second pulse. Similarly, second pulse arrives, it disconnects the AND gate. And again, third pulse will arrive, which again make the AND gate turn on, and the continuous pulses for a precise time interval will start. Now you tell me, and it will give the decimal value, which is displayed in this counter. So first pulse, this is number one pulse. Second pulse, it is not there. This is the third pulse. I mean, according to this, right? So this one pulse, two pulse, three pulse. This is the fourth pulse is not there. Again, you will be having five pulse. Okay, so the thing is going like this. So first pulse is allowing the AND gate to turn on. After that, when second pulse is coming, then it disconnects the AND gate, right? Because there the signal is low. I mean, the pulses is low. Again, when the high pulse is given, that is on the that is for the third pulse wave. Then again the AND gate turns on. So this process actually continues. Now there is a specific formula for the unknown signal that you can calculate. The formula is somehow F equals to N by T. This is the formula. Okay. So what does it signify? F is the frequency of the unknown signal. N is the number of count that is displayed on the counter, and time T is the time interval between the start and stop of the gate. That is the AND gate. AND gate, I told you na, that when first pulse will be given, it will be turned on. Second pulse is turned off, just like that. So there are some advantages definitely of this digital frequency meter. That first advantage is that definitely high sensitivity. Okay. Very much sensitive, high sensitivity. This is one thing. Second is production cost is very low. Okay. And good frequency response. That is also. Disadvantages there. Definitely this kind of instrument does not measure the exact value. Okay. Sometimes there may be some error, some fault. So it's not possible to calculate the exact value all the time. Okay. Now, here are some digital frequency meter applications also. So applications, you can say it is used in radio, okay? Radio or, yes, radio is a very good application, and it can be used in measuring the parameters like pressure, strength, vibrations, all those things, okay? So this is the working of digital frequency meter. Now, there are various types of frequency meter on the basis of measurement according to the frequencies. Okay, according to the frequency. So we can see that one. Suppose, let me share my whiteboard once. So suppose I'm telling you about number one, that is deflection type. Deflection type, deflection type that is a digital frequency meter, which can measure the low frequencies, okay? Low frequencies, that is to 900 hertz, okay? Second is Weston frequency. Weston frequency meter, which is not deflection type, and it can measure the frequency in the range of 10 to 100 hertz. Okay, these are important. Huh? Next is advanced meter, or you can say digital frequency meter. Advanced meter, we can also say advanced digital frequency meter. This measure around a range of 104 to 109 hertz. Okay, so these are the important part, that which type of digital frequency meter measures which type of frequencies, and that is Western frequency. Okay, so what are the components of digital frequency meter? Can you tell me? Can you sum up the components? And can you tell me?
Yes, ma'am.
Tell me the components. Yes, tell me.
The signal, then Smith trigger, Smith trigger, then
And
in the end of the first line is counter, and second line is
flip-flop, crystal oscillator. Okay. Yes. Thank you, Pooja. So there are many
yes.
components here: amplifiers, Schmitt trigger, AND gate, flip-flop, counter, crystal oscillator, time-based selector. Okay. So every component has its own importance. That is important. Now, so use of Schmitt trigger, I told you why Schmitt trigger is important. That it is can be used as a ADC, okay, that is analog digital converter, and it can act as a comparator circuit. Okay, so the main advantage of this digital frequency meter is that it can measure very small value of frequencies, but yes, disadvantage is again there, that is sometimes exact values does not come. So I hope these varieties are clear to you. Reflection type, Western frequency, and digital frequency meter, advanced type. So the measurement ranges are also important. In objective questions, this will come, the range. Okay, so it is important in respect to that. Now, let me see what is the next topic you have. Okay, 2 topics we have done today. Next, we have high frequency measurement, circuit for frequency measurement. Okay, so in our next class, I will do high frequency measurement. Let me see some problems on digital frequency meter. Wait. Okay, so if you have any query, you can ask me. Today we have discussed 2 topics. So if you have any query, you're free to ask.
No, ma'am, no doubt.
Okay. So tomorrow tomorrow means next class, we will start on the high frequency measurement. Okay. Okay, let me see some problems if I can arrange for you. Wait. Basic circuits we have done. Flip-flop we have done. Sure. Okay. High frequency measurement, that part. Let me just initiate the thing, that what things you have to learn in high frequency measurement. Just a basic thing. Our next topic will be high frequency measurement. Okay, so this will be our next session's topic. So main thing which we have to learn, some of the techniques we have to learn here. First technique that we will learn, that is pre-scaling. Okay. Second technique we will learn, heterodyne converter. Heterodyne, I think you are much aware of this word, heterodyne converter. Okay. Third, you will learn transfer oscillator. Okay. Fourth, you have to learn automatic divider. Okay. Fifth, you have to learn, no, these 4 topics are there. These 4 topics are there. There are techniques for measurement of high frequency. Okay, high frequency, that can be the range of somehow 100 megahertz. Okay, so this about this all this and small portion of frequency spectrum also. So this high frequency has so much of high range, counters cannot count at the speed, okay, demanded by high frequency measurement. So sometimes that becomes a limitation because of the counters. They always uses along with the digital frequency meter, right? You have seen, na, just now we have done digital frequency meter, we are using counter. Counter that can be and the measurement has to be less than 100 megahertz. Okay, then only it can be followed, it can be seen on the counterpart. Otherwise, it's difficult. So, okay, tomorrow's next class, we will discuss with this high frequency measurement, and I will try to complete this chapter as soon as possible because it's a bit theoretical chapter. Next, we'll move on to, after this, doing this part, then CRO. CRO, you're much aware, so I will not spend much time on CRO. Okay, now let me take the screenshot of the attendance because the LMS is down today. Then you can leave the class. Wait. Okay. Thank you so much for attending the class. We will meet in the next session. You can leave the class.